All right, welcome to Filecoin, hosted by Blockchain at Berkeley. We have a white paper deep dive. It's back. So who are we? I'm Nishan,
I'm Robert.
and so when we were making this slide, Robert tried calling me like his master or something, but no, we were both pupils in this race, in this quest for Filecoin. So in terms of questions, just do whatever. You can like type it out in the chat, or like if there's ever a pause, we'll pause after every slide. Just hit unmute and hit us up with any questions. Both is good. Um, Thanks, Robert. So here's our agenda. We're going to start off with a little bit about why Filecoin, and also rip Madmen. So why read Filecoin? Oh yeah. So why read Filecoin? So we kind of split it up into 4 categories, and it's all based on just the idea of decentralizing everything. That's the first thought that comes to mind. So first of all, y'all saw IPFS around 3 weeks ago, and Filecoin is pretty much a step on top of IPFS, a layer on top of IPFS as an incentive layer. So IPFS and Filecoin work together in a really beautiful way. Decentralized storage networks is what Filecoin is and what Filecoin creates, and we'll introduce this concept and talk about how awesome it is. Filecoin is also introduces things that make the decentralized web a little more efficient. The network that Filecoin and IPFS are trying to build together, it makes it a little more efficient. And fourth, and most important of all, it's a cryptocurrency. So why not get rich? So we're going to dive into each one of these.
The first, InterPlanetary file system. Just a quick recap from Andrew and Simon's presentation. We basically stole their slide. But it's a file system, right, that distributes and versions large data. So instead of having servers host data and then being able to block access to those, this is basically a distributed file system, file network that enables you to get data in a really non-blockable way. I said that really badly, but yeah. It's peer-to-peer, has no privileged nodes. Nodes store IPFS objects or files in their local storage, and then they connect to each other and transfer objects. So yeah. Although there are a couple issues that come up with that, right? Because there is no really incentive for people to store objects that they're not benefiting off of, right? Think of BitTorrent, for example, where you might have seeders for some file, for some like film or movie, whatever. But as long as if it's not popular anymore, or they don't really get anything back from holding it and sharing it with other people other than, I guess, like clout. So say like I want a background and I find the source, right? And then I save it locally and I don't redistribute or reshare it, right? And then that source that I found, that I got the background off of, goes offline. Then there's nothing for Niche, right, to do after when he wants the background, right? There's no more source and no more generous users to actively host the pinned content. So we're really like relying on people hosting content for like the good of like the network, right? And yeah.
Yeah, I think we'll pause here for a couple of seconds if there are any questions, just if everyone understands kind of what this problem is. All right, I'll take that as we're all good.
Cool. So decentralized storage networks, right? That's what IPFS is. That's what Filecoin is, right? So currently today, why we want them? We currently rely on huge central cloud storage providers, right? Amazon S3, Azure Blob Storage, Google Cloud Storage, right? And we really need to trust that they keep our data safe, right? And so because they're the controllers of this whole network that we're relying on, they basically have the power for everything. And that's not necessarily motivating in the future as we begin to rely on them more and more as more things move to cloud storage, right? And so we can also easily get price gouged because they control the cost of how much of space, right, of data storage. And there's no one to tell them no because they're already so big, right? So with decentralized storage networks, anyone can join. Anyone who has storage can join and become a provider. It's trustless, so you don't have to rely on some central entity to hold your data. You can make sure it's encrypted, make sure it's secure, and ensure you have ways to get it back in certain cases. And you'll always know that the pricing is fair because it's determined by the entire network. And or that's for Filecoin specifically. And then it's a lot more accessible, right, in that sense.
Yeah, cool. So I saw there was something in the chat from Ayush asking about how endpoint security is handled. We'll sort of brush on that, but in the end, the Filecoin protocol doesn't cover this too much. They kind of put the onus on you yourself as a client. If you want your data to be protected, you should encrypt it. But also, there are things that we'll kind of get into about how the data is stored. That is stored in a pretty secure way, and in a way that you can't retrieve your data, your entire file, or anything like that.
Yeah.
Yeah. Okay. Cool.
So, and Filecoin specifically works on making a more efficient decentralized web. So so it introduces a bunch of network buffs to IPFS, or network buffs we call them. So basically, it includes storage locality. So basically, it encourages people closer to the user who wants to host that data, to store their data, to host that data. So if you want to store a file, it'll encourage storage miners or storage providers closer to you to do so rather than farther away around the world. It includes off-chain storage, right? So nothing's actually stored on a network, and so that's a lot faster, right? You don't have to rely on network speeds or just really clogged up systems to host massive amounts of data. It includes pretty useful implementation of proof of work, or it's not proof of work anymore, but consensus that actually moves the network through and actually records data and ensures your validity and so forth. And it provides really good incentives for people to keep staying active and actually providing storage and actually getting your files that you wanted to store.
Cool. So that's the kind of overview of kind of the problem statement, why we're here. I just want to pause for another second for any questions about these 3 points, and then we'll kind of get into a high-level overview. All right, sounds good. So Filecoin is basically a decentralized storage network that acts as an incentive layer for IPFS as its primary function. And it does this by creating two markets. It has a storage marketplace and a retrieval marketplace. So the storage marketplace is where a client, as you can see in the little diagram up top, goes to the marketplace, asks, I'd like to store this file, which is this big, and there's an order matching system. So we'll kind of get into that more, but you can get your order matched and get your files stored by storage miners. The retrieval marketplace is the flip side. So if you're a client and you want to get your file again, there's specific retrieval miners as well, who you can pay Filecoin to get these files from these storage miners. So we do this using some novel technologies from Protocol Labs, which we'll dive into. So there's proof of replication, proof of spacetime, which are both instances of proof of storage, which kind of help and work together to create what we'll call Filecoin Consensus. So kind of the core idea, visualize a little bit, is say I'm here and I have a file that I want to get stored. What I'll do is I'll pay a storage provider, hopefully near me in some locality, some Filecoin to store my file. I'll send that over to him. And he'll keep the file for a specific amount of time, making sure to prove to me that he has this file. Then whenever I kind of want it back, I pay Filecoin to a retrieval miner to get it from the storage provider and get it back to me. Then this kind of represents the concept of locality. So something closer to me, will get more Filecoin for kind of getting it back to me. So that was the high-level overview of Filecoin. We're gonna dig into the main building blocks of Filecoin, and yeah, we'll get started on that.
No questions so far, really quickly. No.
Yeah, we'll check.
I've got a quick question, actually.
Yeah, for sure.
I don't know if Filecoin is like fully released yet, but would you guys happen to know like a ballpark of the rates to deposit and withdraw data?
I'm gonna be honest, I haven't gotten into it too much. I might have to get back to you on that. Yeah,
Yeah,
I don't
that's
want to. I
fine.
don't want to say anything else. Yeah, yeah.
It was
We'll
just gonna
we'll
lead
definitely try.
into a question. Yeah, Dave, I guess it would be market set, but I'm just thinking like if you have to pay every single time you want to store and retrieve data, then it's probably only useful as like cold storage. Like you're probably not gonna want to, you're gonna want to keep that data on your hard drive if you're gonna access it frequently, right?
No, it's the micropayment stream. So it's solving the problem with BitTorrent, where currently like no one's gonna seed you because no one gets paid. They'll just stop when they get bored. So, but if you had some micropayment, then you'd at least be able to fund it.
Yeah,
Yeah,
and
I see
kind
where
of
you're coming from. That's why I was wondering if they knew the rates.
Oh, okay.
yeah, yeah. Good point. And kind of the same reason that you would want to use Filecoin is the same reason that you would use IPFS pretty much. So I guess we could kind of ask the same question that way.
Fair.
Yeah. Thanks, Dave. Yeah, what's up?
All right,
Were
No,
you,
I'm
were
good.
you gonna
Thank
say
you.
something? Okay, cool. Thanks, man.
sweet. So yeah, now moving into the building blocks of Filecoin. So in Filecoin, there is a set of design goals that basically the creators want to ensure. So first off, we need to achieve, they need to achieve network integrity. So that basically means that after a put request or after clients want some file to be put, they can store it in the network, and all they need to retain is some hash of the data, so that they can use this hash to get their data back and then verify its integrity, right? So that it hasn't been changed. So we don't want the actual clients putting their data into the network to have to actually store any part of their data or a large part of their data, right? To be able to verify afterwards. Second off, retrievability. So we need to assume that for some amount of data, for some number of storage miners storing data in the network, we provide some level of fault tolerance. We'll go more into this later on, but basically we need to ensure that there are ways to retrieve your data, so that if you put your data into the network and some storage miner gets it, but then all of a sudden decides to dip out and leave with your data, right? You want to ensure that you have some protection against that happening, and that you can eventually retrieve your data when you want it. So public verifiability and auditability is kind of linked together. So we want to ensure that any user in the network can verify the validity of data stored in the network. It's done through verifying proofs, and we'll go into that more later. But so they need to be able to do that, verify proofs without having any actual access to the data, so that we can maintain quick operations. And then after that, we need to have good incentives. So we want to actually incentivize people to store data and get data and move data around the network, and ensure that it keeps flowing. And there's no place where people are like, oh, I don't want to do this anymore because there's no value add for me to hold this person's information anymore. And confidentiality we need to ensure. And this is kind of the question you asked Ayush for endpoint security. Basically, clients that desire for their data to be stored privately basically need to encrypt their data before submitting them to the network. And past that point, everything is kind of abstracted from the paper or from the actual protocol description we're going over right now. And for how it's implemented, it's dependent, sort of.
Yep. Cool. So I know this is a pretty high level overview, so I want to stop just to make sure we're all on the same place. Does everything make sense? I just want to make sure if there's any confusion or any points, because from now on we're going to kind of start diving into it. So I just want to make sure we're on the right place. All right, cool. So we talked about these values on a high level of what we want, and we can kind of categorize this into a hierarchy of needs in Filecoin. So to achieve what we'll call a DSN perfection, decentralized storage network perfection, we need two things pretty much. We need a concept of verifiable markets. So this is the storage and retrieval markets. And we also need something that's termed useful proof of work for creating Filecoin Consensus. So both of these rely on proof of storage and Filecoin's implementation of proof of storage. So we'll kind of go top down, introducing the problems of verifiable markets and useful proof of work. And then we'll talk about how proof of storage is used to address this.
Yeah. So verifiable markets, basically we need to have, this is just giving a broad definition of what they are and how they are going to be implemented. So verifiable markets include two phases to how they move data around. So basically, there's a phase for order matching, or where users or clients either moving into the storage market or into the retrieval market would put up a bid for storing a file or retrieving a file, and with some money associated with that bid. And then there would be some miner, storage miner or retrieval miner, who would also put up an ask ask order, basically for that file and for that amount of money. And we need to have a way to match these orders and put them together and store that information, make sure they get done, make sure they're held out, and then we need settlement for those actual processes. So whether or not a service was done correctly, whether it's uploading the data and storing it for the period of time or getting the data back, we need to ensure that this has actually happened and that the proper people get paid out for it and the proper people pay for it. That's verifiable markets in a nutshell. And then the next part is useful work consensus. So right now, so to actually achieve that sort of verifiability, a lot of times blockchains use some sort of proof of work, and that's kind of non-reusable, right? And wasteful in this case. For more on non-reusability, miners usually solve hard computational puzzles, right? Inverting a hash for most cases, for example, Bitcoin. There have been attempts to reuse miners' computational power, right? To make it something, to get some more output out of that grueling process, right? Primecoin, for example, finds new prime numbers with their proof of work. Ethereum, they, alongside proof of work, execute small programs. So that's how they use their, that's how they get their smart contracts to work. And then, for example, Permacoin, I don't think this one's been implemented actually. Proving some data is being, no, Spaceman that was. Proving some data is being archived alongside proof of work. So there's been attempts to reuse the computational power that's going towards the hard puzzle to prove work, right? So those are some of those. And proof of work is also kind of wasteful, right? It uses up a lot of energy because you're just putting your PC solving random puzzles, right? Attempts to reduce wasteful work have included Spaceman, right? Where they didn't actually rely on computational puzzles, but rather enforce miners to dedicate this space instead. Although that's still kind of wasted in this case because disks are just filled with random data. So it kind of, it just puts the resource somewhere else that makes proof of work, right? And there's also traditional Byzantine agreement based on proof of stake, which is not computationally impactful, but yeah. Filecoin attempts to address these issues with its proof of storage in this case, and Nish can go more into that.
Yeah, so Gloria, just to address your problem, your little comment, we're definitely not saying that proof of work is bad in any way. Honestly, I think it's great. It's just that there are these little things that Filecoin thinks they can kind of build on top of and make an attempt at kind of making their proof of work specifically a little more reusable and like a little more or less wasteful. So it's no slight against anything like proof of work or Bitcoin at all.
Yeah.
Cool. We all right? Okay, let's see the chat.
Oh, I didn't mean it as like you were attacking Bitcoin, but I meant the reason why it's secure is that it's not reusable and that it's so expensive.
Yeah, definitely. I see that. Yeah, and Andrew, I see your question in the chat about how much is Filecoin concerned with speed of usage. They definitely are. We'll kind of see this built up over pretty much the next half of the presentation. There are a lot of design choices that they make for speed of usage, and we'll talk about considerations at the end about this that affect speed. So they're definitely very concerned. They implement it all over. We'll notice things with the retrieval market and things with our proof of storage. So, and how we build it out. So it'll kind of get answered over time.
Yeah.
Cool. Okay. So this is kind of where we dive into it. So to just kind of recap, here's why we need proof of storage. The big point is that we need to prove that storage providers are actually holding the data that they're promising to. And as we kind of brought up before, ideally, we could do it through useful and reusable work. So to kind of add further motivation, in Filecoin specifically, the creators kind of talk about 3 sources of attack that we're really worried about. So the first is a Sybil attack. So say you have your data store and you can store a file on it. A Sybil attack here would kind of be creating multiple identities on Filecoin and storing it in the same place, but still reaping the reward multiple times more. So that means you're getting more Filecoin, and also you're kind of you're saying that you have way more power in the network than you actually do, which is important for consensus. So that's a very dangerous attack. There's also an outsourcing attack. So this is where you claim to store more than you actually have on your device, but just retrieving it elsewhere. So either just retrieving from the internet or from another storage miner through a retrieval method, just kind of promising to store more than you actually can. And again, that's a very powerful attack because the consensus pretty much depends on your power on the network, in the network. Then finally, there's a generation attack. So this is a little trivial, but it's kind of about having the ability to efficiently generate data on demand. So say there's data that you can actually generate using like a small program, you can kind of promise to, again, store more than you actually can. It's a pretty trivial case though. So basically these 2 things, proof of replication and Spacetime, provide stronger security guarantees because we need this in Filecoin. And so we'll kind of address all 3 of these attacks. So this slide is where we're really getting into it. So please stop me at any time if there are any questions or you need clarifications. Basically, this is proof of replication, the first step in proof of storage for Filecoin. So the players here are the prover, which is the storage miner, and we'll call him P, and then the verifier V. So a verifier can be anyone on the network who wants to check the storage miner. So then so the process starts with the setup step. So here's where a prover, the storage miner, promises to store specific replicas of the data, which are identified by a specific hash. So I just want to go back to one of your points way back, actually, your first question. Data in Filecoin is kind of split up into very small chunks and distributed across miners. So no storage miner will really have any full view of what your file is. So that's one little bit of security, but you definitely need to encrypt your data and take stronger security measures. So a prover, the storage miner, promises to store these replicas of the data. Then what happens in the first step in setup is there's a process called sealing the data. So basically it's a slow sequential computation that they make you do that pretty much makes sure that you are storing it on your device. It's basically a bunch of random puzzles that you need to solve about the data. And it's important here that it takes this long amount of time. It'll kind of address the attacks before. So again, Andrew, this is kind of going into one of your recent questions about what they think about speed. This is pretty much the only place where they're actively being inefficient to stop us from these attacks. And they try to mitigate this with further steps, which we'll see. So we seal the data, and then these
question. Sorry.
Yeah, no problem. Yeah, no worries.
And if this is like too low level, just skip past it. But just to make sure I understand, the sealing step is to check that local storage is actually being used. That's the focus.
Yeah, pretty much. You're making sure that this specific replica is being stored on your device. So the phrase kind of like this specific replica is really important to this. That's kind of where the security guarantee comes in. So this seal measure is kind of it kind of brings out things that are later added to the proof of storage down here, if we see in part 2. So stuff from the seal is added to your proof of storage to prove that you're storing this specific replica on your device.
Gotcha. Thank you.
Cool. Thanks, man. So kind of to reiterate, replicas are signed uniquely to the prover's replica itself, so the specific one that you're storing on your device. This is really, really important. So that nobody except the prover or verifier can kind of replicate or have the full picture of this replica. So that's the setup, and it provides the verifier and the prover everything they need to do to move on to prove and verify. So the prove step in this kind of conceptual world is that a verifier throws a random challenge to the prover based on a specific replica. So in the setup step, you'll kind of learn the space that we're kind of working in the file. So the prover or the verifier knows kind of how to challenge the prover. So it'll say, prove that you know this specific part of this replica. And what'll happen is then the prover will come back with their proof that they hold this replica. So here's where it kind of comes in. This is a little abstracted, but all you really need to know is that it holds information specifically to this replica. And so from before, the seal operation, along with other things, kind of mean that you have to fully store this replica to create this proof. And each challenge only corresponds to one correct proof. So then in the third step, in verify, then this is passed over to the verifier. And here's where they check that the proof is fully correct using the challenge and the hash of the data. And any replica specific identification. So that's actually a type over there. It's not the pub key, but replica specific information. And that's kind of where this gets wrapped up in this proof of replication. Does this make sense to everyone? I can definitely reiterate any part of this. I kind of liken it to kind of a game of pinball where the replica or the verifier kind of throws different challenges and the prover kind of has to keep coming back and showing, yeah, I have this, yeah, I have this. So yeah, are there any questions about this? Okay, sweet. So I use the word concept in this because there are definitely some inefficiencies about this. The idea of continuously going back and forth seems kind of weird, and there's this really weird seal operation we will have to keep, but we want to do things to just kind of make this easier. So this is where proof of space-time kind of comes in. So we have proof of replication, but that's only for a specific instance in time. So it might we might know it like time step t equals 5. That okay, they have it, but say you want to keep you need them to keep the data for much longer. How do we do that? So we could repeatedly challenge with proof of replication, but that's going to be very slow, and we really don't want that. So this is where proof of space-time comes in. And so the biggest thing about proof of space-time is that it's non-interactive. So in proof world, non-interactive kind of means that the prover is able to do everything on their own side without a back and forth between the prover and the verifier. So what basically happens is we'll create sequential proof of replication proofs for a specific range of time. So this diagram on the bottom is pretty useful for this. So with the proof that you get out of one step, you're kind of building on top of that as you go around to create the next proof. And so basically in each iteration, you generate a new challenge randomly using a hash function. You generate the proof for that. So you get the challenge, you generate the proof, and then you kind of put it all together. And yeah, so that's basically how that works. To help us kind of compress size, we create snarks. So these are kind of compressed into a snark proof. So these two things, Andrew, are part of how Filecoin kind of thinks about network inefficiencies or trying to make things a little more efficient. We have this non-interactive protocol now. So what happens is a miner chills by themselves, goes through proof of space-time, creates their proofs. And when the network calls on them saying, okay, I need you to prove that you've held this data until this point in time. So not just right now, but this whole time you've had it. They're able to show this proof, and the verifier is kind of able to unroll it and verify that. Yeah, it's proof of space-time is really cool. Let me see. So yeah, so it's up to the network really. So the network is a little vague, but it's kind of any full node on there. So other storage miners can challenge, other retrieval miners can challenge. It kind of happens on a time step by time step basis.
Wait, so is there an incentive for general participators in the network to challenge other people's security, I guess? I don't know.
I think, so actually, let me step back a little bit. There are options that you can make as a as a client who wants to store your data for kind of how secure you want to be with how you're storing your data. So I believe that there's an option to kind of see how much you're trying to like run these verification proofs or like check for these verification proofs.
And then you'd expect people to have to spend more Filecoins.
Yeah, you'd spend more Filecoin for that.
Thank you.
Cool. Does Proof-of-Spacetime make sense to everyone? Okay, sounds good. I think it's really cool. This kind of brings it all together. So now that we have this, I'm just going to follow up on our motivations from before. So now we can be fully assured that data is stored over time. If we look at the 3 attacks, the specific things that I kind of highlighted in proof of replication and spacetime kind of address this. So for Sybil attacks, proofs rely on replica-specific identification. So you'd be able to tell if different identities are kind of using the same replica, or if there's any kind of manipulation in that way. It's very similar for outsourcing as well. You can tell where and who is exactly storing this replica. If it's kind of being taken from somewhere else, you can kind of tell that. And then for the generation attack, something that specifically helps us against this is that there's a seal operation that forces us to store the full data. Seal is kind of used everywhere as a security guarantee, but I just wanted to highlight it for generation. Yeah, how does that sound for everyone? Okay, sounds good. So now we're gonna take our proof of storage mechanism and add it to our verifiable markets and our useful work consensus and kind of see how it all fits together to create the Filecoin network.
Sweet. So let's first start with the storage market and what happens there when when people want their files to be exchanged. So there's an on-chain order book for holding bid orders, ask orders, and then deal orders. To go over those, so a bid order is something that comes from a client where they say they have this file that's 2.8 terabytes, right? Or they want to pay 1.72 Filecoin for it. They want to store it for some sequence of time. They can ask. They can also define the actual how overstored it is. I'm blanking on the word, but they can define how much collateral is needed for this piece, and I'll go over collateral in a second. Basically, how much storage miners need to put down so that they can ensure they're storing the data. So that's a bid order, what the client basically does, and that's the first step of the order matching in the storage market. After that, storage miners also put up ask orders. So they're saying, I have this much space. I'm going to basically expect a return of this much Filecoin for this amount of time. And when they do this, when they put out an ask order, they're also going to put out some collateral with that amount on it. So that if they don't adhere to their terms that they're putting out in their ask order, they're going to be penalized and lose that Filecoin that they're putting up ahead of time. So after bid orders and ask orders are put together, they're matched together using classic order book schemes. So we're not going to go really into that. But basically, once a deal order is made, the actual exchange happens. And then that's how orders are actually matched. And after that, going over settlement, basically this is what Nishan was talking about with proof of storage. So we need to actually ensure that this deal is being is actually happening, right? So when a storage miner fills a sector, they seal the data and then they submit proofs to the blockchain. And Amira, for how often they verify and prove that they're storing it, every epoch, so every block, every timestamp, they'll basically put up a proof and put that onto the blockchain. Basically, if any of these proofs are missing or invalid, they're going to get penalized for this, and they're going to lose part of their collateral. And then when the time of the order is expired or the funds run out and the service was provided was correctly provided, right? The storage miners are then going to process their payments and remove the orders, so remove the files that they're storing, and basically get the Filecoin that the initial client put up at the start. Does that make sense? All right. So then we can move on to retrieval market. In the retrieval market, it's sort of similar, just that now it's an off-chain retrieval order book. So this is going to the actual speed and the, I guess, the speed of the use of the retrieving data back, right? And it's it falls into line with the locality, benefit of locality for storage purposes, right? So the order book isn't held on chain, but rather off chain. So retrieval miners will have their own order book of bid orders from clients to get their files back. And the closer they are, the more efficiently they'll be able to basically fulfill these orders. And then what actually happens is bid orders are placed, and then retrieval miners will put up an ask order, which is more similar to a bid order. In this case, it's a file and then the size, the file size, and then the specific file, and then how much Filecoin for this retrieval that's going to be paid out. And then basically you split up into small parts. If one party stops sending, you can safely end the session, and then payment channels will basically redirect payment for the data that they're getting. And this one's retrieval market's a bit more intuitive. It doesn't the verification in settlement comes from basically the clients verifying that their data that they're receiving back is the actual data that they needed. And that's how retrieval actually happens within the network. Any questions on that? No, we can then move on to the general, or actually, Andrew just asked, do both parties need to stake Filecoin into the payment channels too, or do they just pay per packet? So is this in terms of, the retrieval market? So for retrieving, the clients need to stake a coin, and then I'm assuming, Nish, correct me here, that retrieval miners don't put up collateral like storage miners do.
Yeah, I think that's pretty much the idea, just a little different. The second bullet point kind of answers this. So here it's different than with the storage market. So it's basically the paper packet thing, where the retrieval miner and the client set up a payment channel where we pay per packet, pay per small amount of data that's kind of split up. And if anyone kind of stops sending, then we can kind of end the session. And then we'll just kind of end from there. So it won't ever be like someone gets scammed in this. Yeah.
Well, that's a little strange though, because what if the retrieval miner just like decides to send you half of your data back and like ransom you into paying for the rest of it?
That's interesting. I think that's on the protocol Filecoin itself to kind of establish the infrastructure to create this, so that you can't just send different like varying sizes, or like send it in totally different ways. I don't know the full answer to that, but I believe it's kind of on Filecoin to create the infrastructure to that. Does that make sense?
That's interesting.
So
Yeah, I would figure they just
really
have you like stake money into the channel, so that if you know the retrieval miner doesn't send you back all the data, you can just like call them out on it and get their stake.
Yeah. It's kind of interesting, but that isn't how it's done here, interestingly.
Okay, yeah. I can look into it later.
For sure.
All right, cool. Any other question? So then both of these come up to basically create the Filecoin Consensus idea. So the main idea, so to actually motivate these markets to work, the blockchain actually needs to be verified and actually agreed upon. And so miners for the blockchain will actually have a sort of stake to who's actually putting up a new block and such. And they get stake with the amount of storage that they have on the blockchain, with the amount of storage that they have in the network as a proportion, right? And so the blockchain needs to submit and verify proofs of storage so that the storage market can actually be settled and the orders in the storage market can be settled. And then that's done so that, the storage market order book can be maintained and completed. A miner is elected as a leader in every new epoch, an epoch being a new block. And that's based on their stake or storage within the network as a proportion of the total storage of the network. And so a block contains basically the proofs of spacetime, the orders, and anything else needed to update the order book and allocation table. So that's basically it.
Dope. And does someone have a question? Okay. I just quickly looked back at it, Andrew, about the idea of like putting up collateral on the side, or like depositing your funds on the side of the client, and it just confirmed what I was thinking. So a client kind of puts up money and kind of puts it something in like kind of a third party on the storage market. So kind of how I talked about clients depositing funds as a commitment, that's where they do it. But I'll say in the retrieval market, if say there's kind of incentive on both sides to go with the small packet-based paper packet thing, because if say a retrieval miner kind of sends half the data and kind of asks for the client to kind of send money back, like that's totally on the client to kind of do that. So if they're trying to ransom the client out, the client can always end the session, and then they're just done with they come out with half the data, while the retrieval miner doesn't really get anything back. So yeah, I think I'll put it on kind of how the payment channel is set up. Does that make a little more sense?
Yeah, I guess the miner just loses money by like keeping that data there and never sending it back. So they're not really incentivized to do that.
Yeah.
Yeah.
And there's always another retrieve. The idea is that it's going to be more than one retrieval miner, right, providing this service. So they don't necessarily have to go through the malicious one the next time around.
Cool.
Yeah.
All right. So that's pretty much it. That's the setup in Filecoin. So now we're just going to talk about how it's doing right now and just evaluate it for a little bit. So let's just kind of go over the pros and cons. The biggest pro is that Filecoin is really making a good effort at being IPFS's missing incentive layer. So there was that whole problem statement about trying to get random people to pin your files. There's no real incentive to do that. That's where Filecoin kind of comes in. Other pros kind of include reliable storage options. So there are a lot of options and ways to tune the fault tolerance of the files you want stored in the protocol, which is very nice. And this kind of brings up, Filecoin also brings up the concept of competitive pricing. Rather than with more centralized storage providers, there's an idea of the market and the network kind of setting the price, which is an interesting concept. There are some drawbacks. The first major one is that there's a decent barrier to entry in the network. To even become a miner, you need to put up collateral and put up Filecoin yourself. So you kind of need to have Filecoin to kind of start out. It's kind of interesting, but it's part of the protocol. As we kind of talked about, Andrew, there are protocol inefficiencies. So proof of replication has this really long CL computation, which feels pretty weird. And in the retrieval market, there are also inefficiencies with payment channels as you try to scale up. So there are worries around there. I will say that there's continued development around this. There's a lot of development on proof of replication to try and make it a little better bit by bit. So it's definitely a work in progress. And then finally, there have been some poor governance choices with their ICO. They were a little weird with it. They distributed it out in a weird way, kind of prioritizing protocol labs partners, and people think that they kind of asked for more than they really should have in their ICO. So interesting choices there, and just something to keep in mind. But kind of looking forward, there are a lot of cool things going on with Filecoin. So right now at this point, there's about 5 petabytes stored, and they're aiming for a mainnet launch somewhere late this year. So that's really great to hear. Then on the developer side of things, there's a lot of work being made on a community grant program. So there's a lot of current work going on there on stuff like proof of replication and working with large scale storage miners, stuff like that. There are a lot of cool kind of things that we can get into that people are working on, like Filecoin block explorers and Filecoin visualizers and stuff like that. So it's very nice. And also they're kind of working on bridges into existing blockchains. So a lot of current work. I have this random picture here because last month they also spoke in Congress, which is kind of interesting. But yeah, let's see. I see something in the chat. And yeah, that's definitely part of it because they're funded by A16Z. But yeah, so that's kind of how we look at it, how we look at Filecoin. Any questions just about anything?
I will add the cool thing about the just a bit more on the fault tolerance thing. So when you're putting up your files, you can specifically define how many times you want it to be replicated throughout the system and how spread out you want it to be. So you can ensure that for some number M miners in the network, you can ensure that you can specify the number of faults that you want to be able to withhold, or basically survive. Make sure your data survives. So that's pretty cool. But yeah.
All right. If you can get them to speak, that would be amazing.
That'd be dope.
I would be so down. Okay. Let's see. All right, if there aren't any other questions, that's pretty much it. So thank you for coming and listening to us rant about Filecoin.